Hi everyone, my name is Ujjwal Tamrakar and I'm a postdoc working at Sandia National Laboratories. The title of the presentation today is Optimization-Based Fast Frequency Estimation and Control of Low Inertia Microgrids. So in this paper, we propose a framework to provide fast frequency support using energy storage systems. More specifically, we propose a combined approach using a moving horizon estimator and a model predictive controller. Moving horizon estimator is intended to improve the stability of the controller, while the model predictive controller provides a flexible framework to provide the desired quality of service. So the quality of service in this paper is defined as the reduction in the frequency deviation and the rate of change of frequency. And the proposed framework helps us to achieve this flexibility. So if a low quality of service is enough, the power and the energy requirement from the energy storage system will also be less to provide that frequency support, and the corresponding energy storage degradation and the cost will also be low. However, if you want to provide a higher quality of service, the power and the energy requirements will also be higher, and the degradation and the cost of the energy storage system will also be higher accordingly. And all of this is bounded by the physical limits of the energy storage system. So the proposed model predictive framework gives us a platform to implement such a flexible framework where we can provide the desired quality of service while ensuring that the energy storage is within the physical limits of the energy storage system. So this is the combined MHE-MPC framework that is proposed in this paper. So we can see we have a power system here, and we are taking in the frequency and the rate of change of frequency measurements with a PLL. You'd notice that the PLL does not have a low pass filter here. Instead, the filtering is done through a moving horizon estimator. So the moving horizon estimator provides the frequency and the rate of change of frequency measurements without significant delays. These measurements are in turn used by a model predictive controller, which is able to incorporate the physical constraints of the energy storage system, and it also allows selection of weights, which provides this flexible framework that we have discussed before. So this proposed framework is tested in a modified test system from Cordova, Alaska. So we have a small microgrid here with two substations. In the first substation, there are 3 diesel gensets, and in the other substation, there's a 1 megawatt PV plant. It is also assumed that there's a 3 megawatt energy storage system connected at the first substation, and the proposed framework of the proposed controllers are implemented within this energy storage system. The simulation results have been tested for a 2 megawatt step change in load at this substation here. So in this first set of results, we show the performance of the framework when we vary the value of R. So R controls the amount of control action. So we can see that when we use very small values of R, there's a considerable reduction in the frequency and the rate of change of frequency. So this means we are achieving a higher quality of service. However, because of the low value of R, we can see there's a higher ramp rate and higher amount of peak power used from the energy storage system. So there is this trade-off when selecting R, and we can thus control the flexibility of the controller by selecting these parameters. The second result here shows the advantage of using the moving horizon estimator instead of the low pass filter. So for similar settings, we can see that when using the low pass filter, there is oscillations in the system. But if we replace the low pass filter with a moving horizon estimator, the oscillations have been removed. This is mostly because of the fact that the MHE is able to avoid the delays that would be seen when using a low pass filter. So in conclusion, we proposed a framework that can provide frequency support, uh, which is able to provide flexible operation based on the resource availability and desired quality of service. The framework is able to incorporate the physical constraints of the energy storage system into the framework, and is also able to avoid delays, which improves the stability of the controller. In the future, we'll look at verifying the applicability of this approach through real-time implementation, and also try and incorporate parameter estimation to further improve the performance of the controller.